So, Introduction to Public Transport Planning. And I want to talk about what is a good public transport supply, what are optimal solutions. I want to talk about characteristics of public transport. We talk a little bit about terminology, and I will conclude with the planning task. Now, what is a good public transport supply? I guess for you, it's quite clear. We are travelers, passengers, travelers have certain expectations. An important information or requirement is time expenditure. How long does it take? Then directness, different to cycling. It's not the detour in terms of deviation. It's more, do you have a transfer? Do you need to change lines? It's about the availability. How often can you use public transport? Every 5 minutes, every 10 minutes, once an hour. It's about reliability, and we agree that this is important. It's about safety, maybe accidents, but especially in urban public transport, harassments may be a problem. Comforts, are seats available? Is air conditioning provided? Are the vehicles clean? And costs, how expensive is a journey? I now switch to Menti to ask you some questions. And for that, I move to the next set of questions. Before you do something, wait a little bit. This is a tricky one, but we are engineers and mathematicians. We know how to handle that. What I want you to do is that you think of your typical way to work or university. And now you see 5 modes. And the first thing you do is you, I don't know what it says. It says, skip, probably. It probably says skip. Skip this mode, and you skip all the questions until you come to your mode of transport. So if that was, for example, public transport, then you have 2 slides, two sliders, and you input the travel time you need door to door using public transport, x-axis, and the travel time car, if you use the car to do the same journey, even if you do not have a car. So in the end, everybody is inputting 2 values, travel time, public transport, for your journey to work or university, and the same with travel time, car. And you skip all the modes you're not using. Okay? That's a lot of skipping. You see how I can analyze the values later. So, well, imagine a diagonal, everything which is below the diagonal, like our 4, means that travel time in public transport is longer than travel time with the car. Now, we see that quite a few of us use public transport, and in most cases, it seems like the travel time is longer than the car, but you still, for some reason, you use public transport. And in some cases, maybe up here, public transport is a little bit faster. We can look at other modes. This is the car. Yeah, you see in our group, more people use public transport. Car, Well, you see this right at the bottom. Obviously, car is favorable here. And well, I'm not quite sure about the points right at close to zero. This is probably people who did not skip, but I'm not sure. Okay, and then we have people walking. Walking is probably closer to the left because we don't walk long distances. And see if, okay, quite a few people are cycling. Okay, so public transport and really so many people cycling. Interesting, good. And you cycle because public transport is slower, maybe, I don't know. Okay, so this is your personal mobility. Now, what is good public transport? Think of urban public transport, and you can now input values, frequencies, the number of services per hour during peak hour and during off-peak hour. And you can choose between a value between 1 and 12. 12 is every 5 minutes. Maybe you want even more, but look at a typical origin-destination pair. What do you think we should achieve in our cities? So we say as a politician or as a user, this is a good quality. So we see that many of you think that every 5 minutes is what we should try to achieve. And then the second largest value is every 10 minutes. This is 6 times per hour. And for off-peak hours, the majority of you believes that we should have also 10 minutes in off-peak hours. Some go down to fewer services per hour. So this is frequency, and I guess we all believe that frequency is important. Now, accessibility. How long do you want to walk to a bus stop and to a metro stop? And I'm talking about maximum distance. Of course, on average, it will be shorter, but if you allocate stops, where would you allocate them to say that is an acceptable distance in an urban area? So that means, I don't know, something like 99% of your population should reach a bus stop or a metro station within that distance. Okay. So here it looks like that most of you go for 500 meters, and here most of you think that 1 kilometer is acceptable as maximum distance. But we have something like 250 meters, 300 meters, everything in between. I don't know, I guess you know that the more stops we have, the shorter the access distance, but at the same time, the vehicles have to stop more often. And it's always something we need to discuss what is more important, short in-vehicle time or short access time, access distance. Okay, so remember 600 meters, 400 meters. Tomorrow we will look at some of those values again, what certain guidelines may say. And the last one, it's the most difficult one. Look at the trip time ratio, public transport and car. So if you divide, imagine you travel 60 minutes by public transport, 30 minutes by car, then the trip time ratio would be 2. Now my system cannot handle real numbers. It's an integer program. And so you have to find a solution for that. And for that reason, I decided that 5 is equal to 0.5, 10 is equal to 1.0, and so on. I'm very hopeful that you can handle that transformation. So, what is your expectation for peak hour if you travel from suburbs to central business district? What is your expectation if it's off-peak hours in the evening, at nighttime? And what is your expectation for tangential trips? So from maybe not from suburbs to suburbs, but from somewhere in your city on the outskirts to some other place. So you're not going to the central business district. So everything which is lower than 10 means that you expect public transport to be faster. And everything which is higher than 10. So, but you see that the values we get, they vary a lot. So some people assume or find it realistic that car is faster at night. Some also believe that for peak hours and for tangential trips. Now I'm just, well, it doesn't show me any scale here. So that is something probably, if this is, that's probably something like 15. So 50% longer travel time, and some of those say twice as much travel time in off-peak hours. Okay, so that was a valuable input. Thank you very much for that input. And now I go back to my slides. Let's look at the movement. Let's look at the movement of a car, which I call private transport and public transport, PUT. And well, if you travel by car, you park your car somewhere, maybe close to your house, so you walk to the parking lot. In the inner city, you have a feeder road, then maybe a main road. If you travel longer distance, after some time, you will reach the motorway. You will travel at higher speeds until you reach your destination, or at least your destination town. You decelerate, and maybe you search some time for parking, and you have an egress time to the destination. So the components of our time is access time, in-vehicle time, maybe certain delay times at intersections, and parking search time, and we have egress time. If you do it likewise for public transport, well, you also have egress time. You walk to the stop, which is usually further away than a car. Then you wait a little bit, which we call origin wait time, depending on how risky or how risk averse you are. You add a little bit of buffer or less buffer time. Then you have in-vehicle time to the next stop. There you have a transfer wait time. And if you're traveling longer distances, but also on a commute, maybe you take the local commuter train or the high-speed train. On that part of your trip, you may catch up compared to the car. And then you slow down again, you go back to the bus, the last mile with the bus, and then you have egress time. In the end, in most cases, as you see here, it is very difficult to be faster than the car. If you want to be faster than the car, we need to have congestion, or we need to have a large section where we have high-speed rail, or also urban rail can be high speed if you have an underground, for example, compared to the speeds you can achieve in cities. So the components or the indicators of a movement is access time, origin wait time, in-vehicle time, transfer wait time, egress time. And if we sum it up, it's trip time. And if we do public transport planning, well, to a certain extent, it helps us if we can minimize all of those time components. And you see that they depend on different things: the number of stops, access time, in-vehicle time, on the way you organize your lines, transfer wait time, coordination of your timetable. And another indicator which is important in public transport is the number of transfers. Now, what is a good supply quality? It is common in transport planning to use the concept of level of service. So here you give grades, A to F, and that stands for excellent quality, good quality, up to insufficient quality or inadequate quality. Now, whenever we give grades, and we all know from university, to a certain extent, it's subjective, and it depends on the expectation you as teacher may have concerning your students. And likewise, it's with transport. So what is a good transport supply depends on the expectations in a country. You may have more developed and less developed countries. Now, what I show you in the following is taken from German guidelines, so German expectations. When we do planning in Germany, we first start without grades. And this is something, I guess you do it in many places, because public transport is a basic service. We want to provide mobility to people. It means people should get to shopping places, they need to get to hospitals, to schools, and for that we want to provide them with the possibility to travel. So in Germany, we check whether people from their residential areas, if they can travel to the nearest local town or a town with regional importance or a city with interregional importance, so this would be a bigger city, in certain times, because the idea is that in this local town you find shopping, you find a school, you find a doctor, you find a pharmacy. And if you travel a little bit longer, you reach university, high school, hospitals, and longer even a university. And if you look at those values assume that public transport takes longer than private transport. This is objectives we have, understanding the reality that it's really hard, especially in low density areas, to provide fast public transport. The car will probably be faster. Now we are also looking at the interconnection between places. So two major places, maybe Frankfurt and Munich or Stuttgart and Berlin, they should be connected with a certain quality. And here, if you look at agglomeration places, that would be places like Munich and Stuttgart, they are further away. But here it changes. The longer the distance, we expect, or we want to design our networks in such a way that public transport, and we are talking about door to door, not station to station, is equal compared to the car. So this is the first thing about quality. We provide basic services. And even if you do not have a car, we want to provide mobility within that range. Now, if you want to compare different origin destination pairs, different trips, it depends on the distance. If you travel short distance, you cannot speed up that much. You will not use a high-speed train. If you travel 500 kilometers, this is a different story. So this is why for evaluating individual origin destination pairs, we developed a scheme where you look at the direct distance as the crow flies. And for that, we evaluated with a direct speed. So you have the direct distance divided by the door-to-door trip time of a specific mode. And well, then you see that we expect certain accelerations. And Here you see if your direct speed is around, well, above 80 for 500 kilometers, we say that is decent. This is an excellent service. Maybe you can do it faster, but this is what we want to achieve if we provide the grade A. And if you need longer than this time, which is related to a speed of around 40 to 50 over 500 kilometers, then it's level of service F. Now, don't get confused because you think the speeds are too low. That is direct speed. The actual speed you need to drive is usually 30–40% higher because you have certain detours. And then if you look at your car, the speed you need to travel faster than 100 to finally achieve grade A. So this is how we do it, but there are other indicators because, and I asked you about that, we want to make public transport competitive. And for that, we have the trip time ratio. This is what you just voted on. And we all agree that if the value is below 1, it's good. Public transport is faster. But if you're just looking at relatively short distances, 2 kilometers, 4 kilometers, you always need to walk to the stop. You have a certain waiting time. Maybe you need to take a transfer. This is why we would still expect that a travel time ratio of 2 may occur. And you can't do anything about it. It's still good as long as you're not putting restrictions on the car. It is difficult to beat the car on short distances. If you travel longer distances, this changes because you can catch up, and we are looking at the ratio. So this is the second indicator we are looking at. And a third indicator you may want to look at is the number of transfers. Now, of course, it's ideal if you do not have any transfers. So grade A is if you have below 1 transfer. But imagine you travel long distance to a big city, to the capital city of your country. In my case, that would be Berlin from Stuttgart. That is by train something like 6 hours. I take the bus. I have to transfer to get to the station. So I have my first transfer. I transfer to the train. And maybe in Berlin, I have another transfer. So if I have 3 transfers, that is pretty good. I probably cannot do it with below 2 transfers if you travel long distances. And even if you have 4 transfers, it's still something we would probably accept to use public transport. So again, it depends on the scope of your planning, whether it's urban planning or long distance planning. Here you see how this could look like an evaluation which was done some time ago in Germany for the future train system. So they did public transport planning for the train system, and this was finally the solution they got. It's not yet implemented, everything you see here, but it's what they want to achieve. The colors stand for the level of service. Green is very good and red is poor. So in that case, you can evaluate a transport supply. Next point, optimal solutions. We want to optimize things. We want to minimize travel time. We want to minimize access time, maybe number of transfers. We also probably want to minimize cost. Now, optimal solutions in transport, if you talk to politicians, it's always, and to normal citizens, they always tell you, we want an optimal solution. Let's do it right. Your mathematicians provide us with optimal solutions. Now, the thing is that there are no optimal solutions. There are several optimal solutions. If you look at public transport, for example, you can, if you develop a network, it's easy to provide a very good solution if you have enough money. But usually we don't have enough money, so we need to save some money. So we cannot offer a maybe 10-minute headway. We need to go to the 20-minute headway. So in the end, we ideally find a solution which is on this red line and not somewhere up here, but along this red line, the solutions are more or less equally good. And we need somebody to decide what is optimal in that sense. And you have that in all other parts of our life in transport. Mode choice. If you talk to people, they like the car. Why do they like the car? Because it's faster and it's individual. You don't need to share it with somebody. But it needs more resources. So if you want to save the fuel, reduce emissions, it would be more optimal to have collective transport. This is resource saving. And whenever you do that, well, you need to go to walk to the stop. You need to share the vehicle with other people. You need to understand the timetable. So again, what is optimal? What do we provide in our cities, in our countries? Spatial planning, land use planning is a similar thing, and it's very much linked to public transport. If we just live in low density suburbs, it's really hard for public transport to collect people. At the same time, you need more space, you need more resources, you need more roads. So being individual, having your own nice house is maybe nice for you, low density, but it requires more resources. So for public transport, it would be better if we lived all in houses densely populated in urban areas. And you can continue that. Traffic lights, bus priority. Who gets priority? The bus, the pedestrian, the car? Same question. If you want to make traffic lights more intelligent, and this is what people expect from us, it's difficult to make them more intelligent because a car driver would say an intelligent traffic light gives green to the cars, and a bus driver would expect the same for the bus. So what we have is what we call Pareto optimal solutions. If you have solutions which are evaluated with 2 or more criteria, we have more than one optimal solution. And here you already see some results of our work. We try to find solutions for public transport networks, and this is what we will do together tomorrow. But here you see algorithmic solutions in blue, and you see solutions from planners. And this is the challenge we have. We try to understand how planners work, how algorithms work. And I just want to show you that, we can have, of course, solutions which are very good. Imagine you have a ride-sharing system, a taxi-like system. It will be very expensive. So the costs per day, in that case, will be 4,800 euros. But you are fast. So it would be very convenient, very close to the car. What we usually have is something like that. We bundle demand onto lines. People need to make transfers. So this is why travel time goes up, because you're not traveling directly. But we need fewer vehicles. So that saves us money. Now you can choose what is the optimal solution for your city. This was done by a planner. Now, if you give it to the mathematicians, the people in computer science, they can optimize it. Optimizing timetable is not fun for a human being. If you give it to a computer program, it may identify that there's not enough demand on the blue line, so you can reduce some of it. At the same time, you shift the timetable a little bit, and it turns out that you can't really see it here, but it's probably a little bit cheaper and even a little bit faster. But it doesn't have the same headway. So that would be a 20-minute headway, and suddenly you have a 30-minute headway. So it's less equal or less regular. We worked on cheap solutions. This is the cheap solution. Looks interesting, but it also assumes a certain amount of cooperation. So not every passenger is allowed to take the shortest path. You have to coordinate yourself. So probably an unrealistic solution, but in the end, it would work if passengers would cooperate. And here you have a solution where we minimize the transfers. So it's a solution where you get very direct connections. Direct, again, is fast. But if you show that network to a transport planner and maybe a passenger, they would say, oh, that looks rather complicated. So understanding the network is maybe difficult. And here we don't have a headway. We just have, well, one service per hour, but more direct. How comes we only have one service per hour? Because it's not a constraint in our algorithm. We can add that to our algorithm, and it's not considered in the perceived journey time. You could add something like waiting time at the origin, and then again, you would get different results. So the first understanding is that whenever we optimize, it's not the one and only solution. We have a set of solutions. And here you find one which everybody would say, oh, that's not optimal. That is more expensive and slower. It's a very simple solution. We just have one line for each corridor of our network. So we have many transfers. But the good thing about this solution, it's very robust. If you have flooding, if you have an accident, you will always find a way around it. So this is something we did not yet capture in our two indicators, cost and perceived travel time. So always bear in mind that there's probably more than what we may think of. Additional indicators, reliability, and we look at that on Friday. Now, if you have to weigh between quality and costs, you see that countries and cities do it in a different way. Here you see, this is what I got on an international level, infrastructure in rail. And you see that we have different cultures or different affordability of different countries. Maybe not unexpectedly, Switzerland wins. If you look at the share of the gross domestic product, they invest the highest. And if you know that the Swiss earn a lot of money, they have a very high gross domestic product, it's even higher if you sum it up in real values. Yeah, Hungary, I was amazed to see that Hungary is high, but in Hungary, the gross domestic product is relatively low. Now, followed by Austria, followed by, no, not by Germany. Germany is pretty low here. Japan is pretty good. But well, maybe would expect more in Japan. They have the high-speed trains. Maybe the local trains are not, I don't know. It's similar to Europe, and the United States are below. This is different states, California, well, Missouri, I guess. So the quality we get and whatever we optimize, we always have constraints. And one constraint, of course, is the money which we have available for developing a transport supply. Characteristics of public transport. If you look at public transport, and you see here German public transport, a bus, an underground, a regional train, what are the characteristics of public transport? It is the system which has the highest capacity of all motorized modes. If we measure it in persons throughput over one cross-section within 1 hour, and we have a certain width. Let's assume it's 1 lane, maybe something like 3 meters. So no other means of transport can transport more people over 1 lane. Maybe if you walk, it could be close to that, but this is why I said motorized modes. Even with cycling, you will not get the same amount. It's energy efficient, but it's not always energy efficient. If you have empty buses in rural areas, it's not energy efficient. So you could probably say, at least compared to the car, if the seat occupancy rate is higher than 40%, then public transport is more efficient in terms of energy use. It doesn't say anything about CO2 emissions because that depends on the type of propulsion. So the vehicles circulate up and down a line. That means we have a low number of vehicles. What people try to do nowadays with ride sharing or ride pooling, we have it. Public transport is the most efficient sharing system. We share vehicles. It provides mobility for people without a car, which is important. And, well, all this is plus points for public transport. But then they have limitations. The limitations come from you need to go to a stop. You need to choose a certain line. You need to obey a timetable. And that reduces individuality. So this is why people often prefer the car. The limitations at the same time increase the efficiencies. And this is something we need to understand. So don't expect public transport to be as good as the car. It will never be as individual. You may have benefits if you have high-speed trains. You may have benefits if there's congestion on the road. But in the end, public transport is something which we give to our city as passengers because we are willing to walk to the nearest stop, which is very efficient because the bus doesn't have to take detours. We walk 300 meters and there we meet. We have lines. Our network is much smaller than the road network. And we agree to travel at certain times, at minute 10, at minute 20, at minute 30, not at any time we want. And we understand that this is maybe with a 10-minute headway not a problem. But if you have a 30-minute headway at night, maybe you rather take the car. So this is what we need to understand, that this is one limitation of public transport, and we cannot promise the people to make public transport as good as the car. This is probably a wish. We have stress factors. Do I get my transfer? Is my train delayed? Other passengers inside the vehicle, well, maybe I don't like them, they smell, maybe I'm not sure if this person is safe to me. We have feel-good factors. We can read the newspaper. I'm not sure if anybody does that, but you can answer your emails or look at your smartphone. You can sleep. And maybe not on the public transport system, but before you may drink alcohol. Some of that may disappear in the coming years with automated vehicles. So we need to be aware of that. You may know images like this. You find it on YouTube, the making of. It's taken in Switzerland. Where else? So you see that the public transport is much more space efficient than the car. Now, we are transport planners. As transport planners, people expect us to provide good quality, and they expect us to shift demand from car to public transport. And if I speak to students, but also if I speak to politicians and many citizens, how shall we do it? We improve public transport supply. This is the expectations. And like you said, maybe make it cheaper, make the fare system easier. This is the expectation, and the expectation is that this will help to solve the problem. Well, I tell you, if you make public transport better, more people will use public transport, but they may not necessarily come from the car. If you want to shift people from car to public transport, you need to work with restrictions. And you can justify in many cases those restrictions, especially in urban areas. We could install speed limits. We could introduce tolling. Maybe not a toll road, rather something like congestion charging, so tolling for an entire region. We can work with prices for parking. So if you don't do that, there will never be an argument for using public transport as long as you can afford a car. And if you go to places like in Germany and you make public transport free, yes, people would probably use public transport more frequently. But there are not that many car drivers who say, oh, finally, public transport is free. Now I can afford public transport. Until now, I could only afford the car. So if you want to change something, always think of the car as well. In the next 5 days, we look at public transport. But don't forget, it's not public transport only. And then some people say that we need to shape consciousness. We need to install mobility culture. So maybe they talk about the next generation, which is you. And the next generation doesn't love a car, they love public transport, they love their smartphone, they will be different. I'm not so sure about that. Now, mobility culture means that somehow it's trendy to use a certain mode of transport. Scooters, cycling, maybe public transport. I am convinced that mobility culture comes from having public transport and having restriction for cars. If you grow up in an environment where public transport is good and where car usage is difficult, your parents will use public transport. You will grow up with public transport. And this changes the mobility culture. If you grow up somewhere in urban America or urban Germany, not urban, rural Germany, where there's little public transport, you grow up with the car, and this is the mode you know. So culture is about what politicians decide, and we get used to it. And this is also an important part in this discussion in that field. I come to some terminology. If we talk about words, what we talk about is lines. I know that some countries call it in a different way. They call it routes sometimes. Take route A or take route B. In the following, I want to call it a line. A line belongs to a certain transport system, for example, a bus or an underground. It has a name, for example, line number 7 going to university. This line has one or more line routes, so they serve a sequence of stops. And on that sequence of stops, we have something we can call a time profile. So this is the time you need between the stops. We call it a time profile. And that is the basis for our timetable. A timetable is a schedule of services. Now, if you look at one, here you have a graphical timetable. So we have the spatial axis and the temporal axis. And if you look at one of those lines, we call it a service run. A service run starts at a terminal, serves several line stops, and ends at a terminal. We not only have service runs, we also have empty runs. For example, we have pull-in, pull-out services from the depot to the first stop. We have sometimes interlining runs connecting two lines. So this is timetable. Then we have a vehicle schedule. The vehicle schedule, we will talk about that in more detail. describes the sequence of service runs which are served by one vehicle. So one vehicle, for example, the red vehicle, serves a set of service runs. And likewise, we have a duty schedule. Duty schedule is linked to the labor. Anita called it crew schedule, maybe one or more person. And you see that our buses, they operate all day through, but human beings, they need breaks. So this is why we work in shifts. And this is what we describe in a duty or crew schedule. If we are more specific, so we have the service run. This is a specific service departing at a certain time, maybe limited to certain days. This service is only operating Monday to Friday or also on weekends. We have empty runs, pull in, pull out, interlining between two stops. We call the time in the vehicle runtime. And we have two types of runtime. Some people call it also running time. We have the runtime between stops. So from the departure at stop N until the arrival at stop N plus 1. We call that runtime, but also the entire service run from terminal to terminal is also, which we call runtime. This is the runtime of a service. We have the dwell time. This is the time until the vehicle, from stopping of the vehicle, opening the door. Then we have passengers boarding and alighting. Actually, better first alighting and then boarding. And then doors close again. And this is what we call dwell time. And we have layover time. Some people call that recovery time. You arrive at the terminal and you need some time until you start your return journey. That is the layover time. We have, if you look at an entire schedule, we can sum up over all services, and that is what we call service time. Some people call it revenue time. This is the time for passenger transport where we can earn revenues. So you can sum it up over all lines, and this is a value for your network. We also have empty time. This is standing time and pull in, pull out time. And if you sum it up, this is what we call operating time, service time plus empty time. It's probably close to the time we have to pay for labor because, well, if there's empty trips, you also need a driver and you have to pay the driver. And we can compute something which we call timetable efficiency. This is service time divided by operating time. And ideally, this value is close to 1, which is not, but that is an indicator how efficient we use our time. So we have, from the perspective of the vehicle, we have a vehicle block or a vehicle schedule, and you see a vehicle pulling out from the depot, providing a service, so the service time, maybe interlining unproductive time to a stop, standing, well, and so on. So this is on the connection between timetable and vehicle schedules. We talk about pull out, pull in, standing, and interlining. Finally, the planning task. What do we do in public transport planning? Well, we develop a public transport supply. Now, what does that mean? We need to determine the location of stops. And we have terminal stops. Terminal stops require certain characteristics. You need to be in a position to turn your vehicle around. You cannot do that everywhere. Then we have intermediate stops, line stops. And the next thing we need to do, we need to estimate the run times between adjacent stops, because we need that for our timetable. What is the runtime of a line or the runtime of a service run? The runtimes may vary between the time of day. So then we build line routes. So line routes describe the spatial course of a line. If we have several line routes, we get a line plan. We now know our transfer stops, and we can compute the network length. And we need to determine frequencies. Frequencies provide us with a headway. How often do we expect a certain line to operate? And all those 4 steps are often combined in one or labeled as line planning. So you could have more specific words like stop planning and frequency setting, but in general, this process is the line planning process. On top of that, in the next step, we do the actual service scheduling. You may call that timetabling. It's a little bit different whether you have frequencies or whether you have precise departure times. With the precise departure times, you get the timetable, and you also define transfers, the connections. What is the transfer wait time if you transfer at a certain stop? So the task of service scheduling is also to minimize the number of transfer wait times, coordinate the timetables. Then we have vehicle schedules. So we just looked at what a vehicle schedule means or what it is. Once you have done your vehicle scheduling process, you know the number of vehicles you need to buy. And you know not just the service kilometers. This is what you already know from the timetable. You know the pull-in, pull-out trips, you know interlining trips. And from that you can estimate or compute operating kilometers. Then we have scheduling, duty scheduling. Once you do that, you know the number of duties you have, the number of shifts, and the operating hours. This is later on related to labor cost. And duties are not yet directly linked to persons. We have drivers, and drivers go on holiday. They have some of them need to work on weekends, but in the end, they should not work more than 5 days a week. So this is why we combine duty schedules to duty rosters, a sequence of duties. And only then we know the number of drivers we need to employ. And all those steps are called operational scheduling, with specific words: vehicle scheduling, crew or duty scheduling, and rostering. Now, if you look at how it's done in practice, it's rather common that we distinguish between transport planning and operational planning. Transport planners, maybe consultancies, they design a line network, a line plan. And they end with saying, oh, we want that line to operate every 60 minutes or every 10 minutes. And then we move to operational planning. Depending on which country and what conditions, under which conditions, legal conditions you work, this may already be done by the operator. The scheduling is something in between, who is actually doing the scheduling, but often it's the transport operator. They do the timetabling, and they decide about the vehicles, which vehicle serves which vehicle schedule, how do we design our schedules. This is operational scheduling. And since those two institutions, planning and operational, are often different institutions, we have a gap. So we have commonly feedback here between stops and run times. Actually, one is missing here, and frequencies. But they focus very much on transport supply, very much on quality. And then we go down to the operator. The operator is thinking more in costs. How many vehicles do I need to purchase? How many drivers do I need to employ? How many kilometers do I have to produce? So they adapt or adjust the timetable in such a way that it allows efficient vehicle schedules and duty schedules. But what we do not have is, or what we should have more, is the feedback between operational planning and transport planning. Because if you design your network in a different way, you may save on operational issues. And if you're not just focusing on operational issues, then you can make your public transport supply better, so it better meets the needs of our customers. So this is sort of the framework of our research group. We want to get those parts together in a more efficient way. You can do it sequentially in optimization, but here it's more like the operational aspect, how we do it in practice, operators and consultancies. Now, if we look at this process and the entire design process, imagine you have to do it for a city. How does the planning task look like? And I called it now an integrated design process. Usually, politicians in some way or society gives you the objectives. So they tell you about expectations in terms of number of transfers and travel times. They may have something like rules on minimum level. You need to offer a service once an hour, a minimum level. This may come from politicians. Or you need to reach the central business district from every residential areas in less than 60 minutes. So this is objectives. But another objective could be something like, we want to be, compared to the car during peak hour, not slower than 50% slower than the car. In the end, we want to have a future transport supply. Now, what do? We develop a solution. This is what we will do in the next days. A line plan, a timetable, vehicle and duty schedules. We put that so that we can work with models in a network model. We will discuss about that after the lunch break. Then we determine the impacts. So for travelers, for example, the times or the number of transfers, impacts on operators, what are the costs, what are the revenues, on environments, emissions, energy consumption, on the society, the service quality, because the society expects us to provide certain qualities. But at the same time, society may need to pay subsidies. So for that, we need an impact model. Impact model is, for example, a travel demand model. And I will show you such a travel demand model this afternoon. So again, we are modeling to compute values we need for evaluating the results. So we have objectives and we want to check to what extent we meet our objectives. For that, we need an evaluation model. If you are a mathematician or a person in optimization, you would probably call that an objective function. So you put everything in one function and you have constraints. In public transport planning and practical transport planning, we also have certain ways to evaluate the quality of a solution, but it may be less formal than you do it with an objective function. Now you look at the result and you look at it and check, do I meet my objectives? Do I have deficiencies? If no, then you're happy that then you achieved your goal. The process ends. But very often the answer is it's not yet good. And then you have a feedback loop. You go back to the development of a solution, and now you can change your line plan and your timetable and the schedules. And this is important for our summer school because we talk about this feedback loop. We can do that in several ways. We can do it manually. We can do it computer-aided. Computer-aided means that some parts you do manually using a computer. For example, you develop a line plan not by an algorithm, but by a human being entering line routes into a computer screen, into a network model. But what you do, the creativity is with the human being and not with the computer. The computer then computes the impacts, for example, the travel time. And then we have mathematical optimization. And my personal evaluation at the moment is that duty schedules and vehicle schedules are ideal for mathematical optimizations, and they are state of the art. This is what we do for decades. Timetables. Many of the timetables are still produced by human beings, but if you really look at it and you observe the process, then you would also say, a computer can do that better. There are certain exceptions. If you look at Switzerland, they have certain methods of doing it. So you probably combine both things, computer and human constraints. With line plans, this is what we are working on at the moment. And probably here, it's still difficult that computers can come up with a solution which planners like. So this is one of our objectives, to develop line plans by algorithms which produce solutions which are, I'm not sure if I should say similar to man-made solutions, but which are competitive. And here, the solution space is so large that until now, we are still working on it. And there's room also for you, if you want to go into that field, to do more research. Of course, there is research in all levels we see here. Whenever you do planning and you're a mathematician, you try to get your things straight. You simplify the reality. You try to build a model which you then can optimize. And you leave everything out which is unnecessary. Now, if you do planning, we often have certain strains, boundary conditions, a framework. So when you start planning, check what you need to do. What modes are you talking about? Are you talking about railway? Are you talking about road and buses? Maybe you're looking at on-demand services. You need to look at the vehicles you have. Maybe you want to purchase them, but those vehicles have certain characteristics in terms of speed and capacity. And if you do it with a certain city, you cannot get rid of the existing operator, even if you think they may be inefficient. You need to cooperate with the operators, and they have certain depots which are already there. So you need to clarify that as input. And you may think of a concept, a public transport system concept. For example, it's rather common to work with hierarchies. Rail, regional bus, local bus. It is a common concept to work with a system headway. So, for example, a system headway in Germany for railway is 1 hour. So we try to match all lines to that 1 hour headway. If you do it in an urban area, maybe you have something like a 15 or 10-minute system headway. But 10-minute and 15-minute, they don't go together. So you need to make a decision, what is the appropriate headway? You can determine certain transfer stops by definition. So not much by planning, where you say, okay, this is the location where we want to meet. And all the trains have timed transfers at that specific location. And then you may think of, when you develop a line route, about optimal lengths of a line route, together with a certain headway and a certain cycle time. So if transport planners develop networks, they don't start from scratch. They have typical modules, line modules in their mind, like Lego bricks, which they put together. And then they always have local conditions, which is the land use structure, the travel demand, the existing road and rail network, cost rates. In some places, drivers are not as expensive as in other places. Yeah, if you hire a driver in Switzerland, that is very expensive. If you do it maybe in Jakarta, it's not that expensive. And that influences the way you optimize. And you have legal requirements. Legal requirements, for example, restrictions concerning driving hours. After 4.5 hours in Europe, a driver needs to take a break. This is something you may need to consider when designing a duty schedule. So, the planning task, if you sum it up, is, if you do it in steps, first question, what is an appropriate system? Is it road-based or is it rail-based? If you have a metropolitan area which has no rail yet, you need to discuss whether you should build a metro-type system. Then the next step, which part of the network is suitable for public transport? Because you cannot use all feeder roads, for example, for a bus. Then which running time should be used for the timetable? Where should we locate stops? How many lines do we need? What service frequency is required? And what type of vehicle is adequate? A short train, a long train, a standard bus, an articulated bus. Now, tomorrow, when we go to actual planning and we plan together, I want to answer those questions. I will to look at all of those questions to give you an idea how we do that, either manually as a planner, computer aided, or later on in the coming days using algorithms. This is the idea. And in the end, the overall question is, how do you or do we design a public transport service that is not optimal? Because now we know optimal is, well, difficult, because we need to define what we mean by that, which is as good as possible, looking at service quality and at cost. And with that, I'm happy, because I didn't know how long it would take me, and I was afraid that I may take longer, but now I'm very much in time. So I can close with this quote: a developed country is not a place where the poor have cars, it's where the rich use public transportation. So this is said by the mayor or former mayor of Bogota in Colombia.